Hi, it's Sleepy Steve, helping you to fall asleep and study. Remember to subscribe to help Steve-O out, and I will keep making more sleepy stories. Tonight, we are going to move quietly into one of the most important ideas in Unit 3 physics, projectile motion. Let your shoulders soften, let your hands rest, and imagine the room becoming still around you while a ball rises into the evening air, slows for a moment near the top of its path, and then falls back to the ground under the steady pull of gravity. Projectile motion can look complicated because the object moves sideways and vertically at the same time. But the calm secret of this topic is that we can separate the motion into two parts. The horizontal motion is treated separately from the vertical motion, and then, when we are ready, we bring the two parts back together to describe the full curved path. A projectile is any object that moves through the air after it has been launched, thrown, kicked, dropped, or fired, and after launch the main force acting on it is gravity. In VCE physics, when we model projectile motion, we usually ignore air resistance unless the question asks us to discuss it. That means we imagine a clean, simple world where gravity acts downward at approximately 9.8 meters per second squared, and the horizontal velocity remains constant. So, in your mind, picture a quiet oval after school. The grass is still warm from the day, the goalposts stand calmly in the distance, and someone kicks a football. The ball leaves the boot with an initial velocity. That initial velocity has two components. One component points horizontally, carrying the ball forward across the oval. The other component points vertically, carrying the ball upward against gravity for a little while. This is the first exam idea to remember. The horizontal and vertical components are independent. Gravity changes the vertical velocity because gravity acts vertically downward. Gravity does not change the horizontal velocity in the ideal model because there is no horizontal force once the object is in flight. So the ball keeps moving forward at a constant horizontal speed, while its vertical speed changes every second. If a projectile is launched horizontally, such as a marble rolling off a desk, its initial vertical velocity is zero. It begins by moving sideways, but the moment it leaves the desk, gravity begins accelerating it downward. It falls just like an object dropped from rest from the same height because in both cases the vertical motion starts with zero vertical velocity and the same vertical acceleration. This can feel strange at first. A marble rolled from a table and a marble dropped from the table at the same instant will hit the ground at the same time. If air resistance is ignored, one marble travels sideways as it falls, and the other falls straight down, but their vertical motion is the same. The horizontal motion does not help or delay the vertical fall. Now, imagine a different example. A javelin leaves an athlete's hand at an angle above the horizontal. The initial velocity is not just one number to use directly in every equation. It must be resolved into components. The horizontal component is found using cosine of the launch angle, and the vertical component is found using sine of the launch angle when the angle is measured above the horizontal. In exam language, you would say that the initial velocity can be resolved into perpendicular components, with the horizontal component remaining constant and the vertical component changing due to the acceleration due to gravity. That one sentence carries a lot of marks because it shows that you understand both the vector nature of velocity and the independence of the two dimensions. Let us slow down and look at the horizontal direction first. In the ideal projectile model, horizontal acceleration is 0. That means the horizontal velocity is constant. The horizontal displacement is simply horizontal velocity multiplied by time. If a ball has a horizontal velocity of 12 meters per second and it is in the air for 2 seconds, then it travels 24 meters horizontally. Notice what made that calculation possible. We needed time. Projectile motion questions often revolve around finding time from the vertical motion, then using that same time in the horizontal motion. Time connects the two dimensions. The horizontal and vertical motions are independent in terms of forces and acceleration, but they happen during the same flight time. Now let us look at the vertical direction. In the vertical direction, acceleration is constant and downward. If we choose upward as positive, then acceleration is negative 9.8 meters per second squared. If we choose downward as positive, then acceleration is positive 9.8 meters per second squared. The direction convention is not the important part. What matters is that we are consistent. At the top of the projectile's path, the vertical velocity is 0 for an instant. This does not mean the total velocity is 0. The object is still moving horizontally. It also does not mean the acceleration is 0. Gravity is still acting downward. So the vertical velocity is 0 at the top, but the vertical acceleration is still 9.8 meters per second squared downward. This is one of the most common traps in projectile motion. Students see the ball stop rising and think the force has disappeared or the acceleration has become 0. But the only reason the ball stops rising is because gravity has been reducing its upward vertical velocity the whole time. At the top, the upward velocity has been reduced to 0, and then gravity continues to accelerate the object downward. If a projectile lands at the same height from which it was launched, the motion has a useful symmetry. The time taken to rise to the highest point equals the time taken to fall back to the launch height. The vertical velocity just before landing has the same magnitude as the initial vertical velocity, but the opposite direction. The horizontal velocity is unchanged throughout the motion. But not every projectile lands at the same height. A ball may be thrown from a balcony, a rescue package may be dropped from a helicopter, or a stone may be launched from the edge of a cliff. In those cases, the symmetry is not as simple, and we must use the equations of constant acceleration carefully in the vertical direction. The key quantities in projectile motion are initial velocity, final velocity, acceleration, displacement, and time. For the vertical direction, we use the constant acceleration equations because vertical acceleration is constant. For the horizontal direction, we usually use constant velocity because horizontal acceleration is 0 in the ideal model. A calm method is to make a table with 2 columns. One column is horizontal, one column is vertical. Put the known values into each column. Horizontal acceleration is 0. Vertical acceleration is negative 9.8 meters per second squared if upward is positive. The time is shared between the 2 columns. Then choose the equation that connects the unknown with the known values. In a VCE exam, this organized method matters. Projectile questions can look messy because they involve angles, components, different heights, and diagrams. But if you separate the motion cleanly, define your sign convention, and keep units consistent, the problem usually becomes much more manageable. Now let us imagine a stone thrown from the ground at an angle. It has an initial speed of 20 meters per second at 30 degrees above the horizontal. The horizontal component is 20 cosine 30 degrees. The vertical component is 20 sine 30 degrees. The horizontal component carries the stone forward, while the vertical component determines how high it rises and how long it stays in the air. The vertical component is especially important for time. If the stone lands back at the same height, we can find the time to the top by considering when vertical velocity becomes 0. Then we can double that time to find the total flight time. Once the flight time is known, we multiply it by the horizontal velocity to find the range. Range means horizontal distance traveled during the flight. It depends on horizontal velocity and time in the air. A projectile can travel further if it has a larger horizontal velocity, or if it stays in the air longer, or both. In ideal conditions, for a projectile launched and landing at the same height, the maximum range occurs at 45 degrees, but real life is affected by air resistance, spin, height differences, and launch conditions. That is why physics always asks us to think about models. A model is a simplified version of the real world that keeps the important features and leaves out details that make the problem too complex. In projectile motion, ignoring air resistance lets us focus on the main structure. Constant horizontal velocity and constant vertical acceleration due to gravity. But the model has limits. A badminton shuttlecock does not behave like a simple projectile for very long because air resistance is large compared with its weight. A tennis ball with spin may curve through the air. A feather falls differently from a metal ball unless there is no air resistance. So in an evaluation question, you may need to say that the model is useful for understanding the main motion, but less accurate when air resistance, wind, spin, or changing forces are significant. Let us return to the quiet oval. The football rises in a smooth arc. At the instant it leaves the boot, it has both horizontal and vertical velocity. As it rises, the horizontal velocity remains steady in the model, but the vertical velocity decreases. At the highest point, the vertical velocity is 0. As it falls, the vertical velocity increases downward. The horizontal velocity continues to carry the ball forward until it lands. If we drew a velocity vector at different points along the path, it would change direction. Early in the flight, the velocity points upward and forward. At the top, it points horizontally forward. Later, it points downward and forward. The acceleration vector, however, is always vertically downward because acceleration is due to gravity. That distinction is worth remembering. Velocity is tangent to the path, pointing in the direction of motion at that instant. Acceleration points downward. Force, if we ignore air resistance, also points downward because the only force is weight. So the curved path does not mean there is a curved force. It means the object has forward motion while gravity pulls it downward. Some students think a projectile needs a forward force to keep moving forward. This is an old idea that feels natural. But Newton's first law says that an object in motion continues with constant velocity unless acted on by a net external force. In the ideal projectile model, there is no horizontal net force, so the projectile keeps moving horizontally at constant velocity. This links projectile motion back to Newton's laws. Horizontally, the net force is 0, so acceleration is 0. Vertically, the net force is the object's weight, so acceleration is downward. That is why projectile motion is not a separate island in physics. It is an application of forces, vectors, motion equations, and modeling. Graphs can also help. The horizontal displacement time graph is a straight line with constant gradient because horizontal velocity is constant. The horizontal velocity time graph is a horizontal line. The vertical displacement time graph is curved because vertical velocity is changing. The vertical velocity time graph is a straight line with negative gradient if upward is positive, because vertical acceleration is constant and downward. When you read a graph question, pause and ask what the gradient means. On a displacement time graph, gradient means velocity. On a velocity time graph, gradient means acceleration and area means displacement. These graph ideas return again and again in physics, so projectile motion is a good place to practice them calmly. Now let us think about maximum height. The maximum height is found from the vertical motion. At maximum height, vertical velocity is 0. So an equation that links final vertical velocity, initial vertical velocity, acceleration, and displacement is often useful. The horizontal component does not directly determine maximum height. It determines how far across the projectile moves while it rises and falls. If two projectiles are launched from the same height with the same vertical component but different horizontal components, they will stay in the air for the same time, but the one with the larger horizontal component will travel further. If two projectiles have the same horizontal component but different vertical components, the one with the larger upward vertical component will usually stay in the air longer and reach a greater height. In exam responses, try to use the words component, acceleration due to gravity, independent motion, constant horizontal velocity, and vertical velocity. These words show the assessor that you are not just guessing from a diagram. You are applying the physics model. For example, if asked why two objects hit the ground at the same time when one is dropped and one is launched horizontally from the same height, a strong answer would say, both objects have the same initial vertical velocity of 0 and the same vertical acceleration due to gravity, so their vertical motion is identical, even though one also has horizontal velocity. If asked why a ball slows as it rises, a strong answer would say, gravity provides a constant downward acceleration, which acts opposite to the upward component of velocity, reducing the vertical velocity until it becomes 0 at the top of the path. The acceleration remains downward throughout the motion. If asked why the horizontal velocity is constant, a strong answer would say, in the ideal model, air resistance is ignored, so there is no horizontal net force acting on the projectile. Therefore, by Newton's first law, the horizontal velocity remains constant. These responses are not long, but they are precise. Physics rewards precision. A calm sentence that names the model and links force to acceleration is often better than a vague paragraph that says the object just runs out of energy or loses speed. Energy can also be used to think about projectile motion. As a projectile rises, kinetic energy associated with vertical motion is converted into gravitational potential energy. As it falls, gravitational potential energy is converted back into kinetic energy. If air resistance is ignored, mechanical energy is conserved. If air resistance is included, some mechanical energy is transformed into thermal energy and sound. However, for many projectile calculation questions, kinematics is the easiest tool. Energy can tell us about speed and height, but it does not directly give horizontal range unless we also know time or components. Good physicists choose the method that best suits the question. Let us take one more gentle example. Imagine a rescue drone dropping a small package while moving horizontally at constant velocity. At the moment the package is released, it has the same horizontal velocity as the drone. After release, if air resistance is ignored, the package keeps that horizontal velocity while accelerating downward. To an observer on the ground, it follows a curved path. To the drone moving alongside it, it may appear to fall straight down. That example helps us see how motion depends on the frame of reference. The physical acceleration is still downward due to gravity, but different observers can describe the path differently depending on their own motion. This is not yet special relativity, just a useful reminder that descriptions of motion depend on the observer's reference frame. Projectile motion is also useful in sport. Basketball shots, soccer kicks, javelin throws, cricket catches, and long jumps all involve projectiles. Coaches may not write equations on the sideline, but the physics is still there. Launch speed, launch angle, air resistance, spin, height, force, and time all influence the result. In sport, the ideal model is a starting point, not the whole story. A basketball has air resistance and spin. A soccer ball can curve. A cyclist or long jumper must consider body position and drag. But the clean VCE model gives us a foundation from which we can understand the more complex world. As you rest now, let the whole idea become simple. A projectile moves in 2 dimensions. Horizontally, it keeps going at constant velocity if there is no horizontal force. Vertically, it accelerates downward due to gravity. Time links the 2 motions. The path is curved because sideways motion and downward acceleration happen together. For your exam brain, remember the steps. Draw or read the diagram. Resolve the initial velocity into horizontal and vertical components. Make a horizontal and vertical table. Put acceleration as 0 horizontally and 9.8 meters per second squared downward vertically. Use vertical motion to find time when needed. Use horizontal motion to find range. Explain assumptions such as ignoring air resistance. And for your sleepy brain, picture the ball one more time, moving across the quiet sky in a smooth arc, not because a mysterious curved force pushes it, but because it keeps moving forward while gravity gently and constantly pulls it down. The model is calm. The motion is predictable. The equations are just a way of describing that calm shape. Sleepy Steve wishes you a great sleep. Don't study too hard. Subscribe for more sleepy stories.